You know, in the world of programming, there are few things more frustrating than a bug that just never ends. Today, we're going to unravel a really beautiful, simple solution to a problem that can bring any program to a grinding halt. We're talking about the infinite loop.
We've all been there, right? You run some software and it just hangs. The little loading icon just spins and spins. Forever. You're stuck. And a lot of the time, the culprit is a silent, hidden bug that's trapped the program in a process it can literally never escape.
So, in programming terms, we call this an infinite loop. It's basically a piece of code that just circles back on itself with no way out. And detecting these things from the inside is a really fascinating challenge. I mean, how can a program even realize it's stuck in a loop if all it can do is just follow the steps of that very loop? To figure this out, we're not going to think about code. Not yet, anyway. Instead, we're going to reframe this entire problem. Let's think of it as a simple race, inspired by one of the oldest fables we all know. First up, meet our slow and steady runner, the tortoise. Now, in our algorithm, the tortoise is going to represent a pointer that moves through our data one single step at a time. Super methodical, super predictable. And here's our second contender, the hare. Quick, confident, the hare is going to represent a second pointer that just zips through the data, moving 2 steps for every single step the tortoise takes. And that's pretty much it. The rules for our race are dead simple. The tortoise goes 1 step at a time. The hare, in that same amount of time, takes 2 steps. This simple dynamic is all we need, and believe me, it leads to a brilliant outcome. All right, let's start the race. Imagine our racetrack is this path of data points. Now, the crucial thing to notice is how it loops back on itself. See that? From E, you go right back to C. So both of our runners, the tortoise and the hare, they're both going to start at the exact same point, A. Okay, after the first tick of the clock, the tortoise just plods along 1 step to position B. But the hare, moving twice as fast, has already jumped 2 spots ahead to C. Just like you'd expect, right? The hare is already pulling ahead. Let's go to the next step. The tortoise arrives at C, which means it has officially entered the circular part of our track. Meanwhile, the hare has leaped from C all the way over to E. The gap between them is definitely getting wider. And now, this is the magic moment. The tortoise moves 1 step from C to D. The hare, who was at E, moves 2 steps, first to C, then to D. And look at that. They've landed on the exact same spot at the exact same time. This meeting right here, that is our proof. It's the signal that tells us a loop exists.
So, that worked out perfectly in our little example. But you might be thinking, hang on, was that just a lucky coincidence? Why are they absolutely guaranteed to meet if there's a loop? Well, this is where the simple elegance of the idea really starts to shine. The guarantee actually lies in a really simple mathematical relationship. For any amount of time they're running, the hare will always cover exactly twice the distance of the tortoise. It's this constant 2-to-1 ratio that means the gap between them changes in a very, very predictable way. Think about it this way. With every single step, the hare gains 1 unit of distance on the tortoise. So once they're both inside that circular part of the track, the hare is basically just chasing the tortoise around in a circle. And since the hare is faster, it has to eventually lap the tortoise. It's kind of like a race car chasing a bicycle around a track. A meeting isn't just possible, it is absolutely inevitable. So we have this really cool, intuitive concept. Now let's see how this whole tortoise and hare race translates from an analogy into just a few lines of powerful, practical code. So here it is in Python. It's often called Floyd's cycle finding algorithm, and you can see our 2 runners right there in the code. We have a slow pointer, that's our tortoise, and a fast pointer, that's our hare. And inside the loop, slow moves 1 step and fast moves 2. The very instant they point to the same spot, slow equals fast, we return true. Boom, cycle found. And just to show you, if we look at the C++ version, it's the exact same logic. The names are the same, the movements are the same. This proves the whole tortoise and hare idea isn't just some Python trick. It's a fundamental algorithmic pattern you can use just about anywhere. Now, I know some of you might be thinking, okay, this is clever and all, but isn't there a more straightforward way? Why not just keep a list of every single spot you've visited? And if you ever try to visit a spot that's already on your list, well, you found a loop. And you know what? That's a great thought. Let's compare that approach. And this table just brilliantly illustrates why Floyd's algorithm is so special. Take a look.
The obvious method, the one using a hash set to remember visited spots, has what we call a space complexity of O of n. That just means the more data points you have, the more memory you need. But now, look at Floyd's method. Its space complexity is O of 1, constant.
Just let that sink in for a second. O1, constant space. It means the algorithm needs the same tiny amount of memory whether the path has 10 steps or 10 times billion. It only ever needs to store the locations of two things, the tortoise and the hare. That's it. And that level of efficiency is what makes it so incredibly powerful. So here's the key takeaway. Instead of using brute force memory to remember every single thing we've ever seen, this algorithm uses pure, simple logic. It's trading memory for ingenuity, and honestly, it's just a beautiful example of computational thinking at its absolute finest.
Which leaves us with a final question to chew on. This entire powerful detection system was built on just two simple rules: move one step and move two steps. It really makes you wonder, where else, in technology or heck, even in nature, do we see incredibly simple local rules combined to create surprisingly complex and powerful global outcomes?